Hello everyone. Today I would like to talk about linear algebra using Python. So let's get started and see some examples. So I'm using the Google Colab and you can follow the same for convenience, and we don't need to install anything on our own computer. So you see that we have the 2 by 2 matrix, and we are using NumPy module in Python in order to create and declare a matrix. So for example, you can immediately run and you see that this is a 2 by 2 matrix where the first row is 1 and 2 and then 3 and 4 for the second row. For example, you might want to create a 3 by 2 matrix and then basically you will have the first row, the second row, and the third row. So we have 3 rows and then basically 2 columns. Okay, again, you can uncomment some of these lines and then let's print it on the screen. So we can observe here that we have the 1, 0, 3, 0, 4, 0. That's our 3 by 2 matrix as expected. Now, what about if I want to create a 3 by 3 matrix? How can we do that? Here is the example. This is the first row, the second row, and as you see, we have a list within a list to create the rows of a matrix. Okay, and we separate them with a comma. So this is actually a nested list in Python, and this is the third row. So this gives you a 3 by 3 matrix. Every time you can verify and then make sure you get it right. What about this one? If I basically have the import numpy as np, then I cannot use numpy here anymore. I should call this as np. Okay, otherwise this statement is going to give us an error. Okay, so now we see how to declare the matrices. Another very common operation that you need to know is how to solve basically sorry, let me comment these. How to solve a simple system of equations using Python. And you see that this is our first equation, 3x1 plus 2 times x2 equals to 5. So we have two unknowns, two variables. And actually you can solve this easily analytically, and you can get the result x1 equals to 0, x2 equals to 2.5. But obviously you want to do this using Python, not analytically. So if we have such a problem, then we need to represent this in matrix algebra in AX equals to B. This is the form that we should represent this system. And you see the coefficients 3 and 2, that's the coefficients of the first equation, and then 1 and 2, the coefficients for the second equation. And then you need to insert the right hand side as a vector. Here this is 5 and 5, and then we can ask Python using again the NumPy library. There is the linear algebra solve function, as you can see. If you bring the cursor on the linear algebra function, it will show you the detailed documentation. And here basically the Gaussian elimination method is being used. So it's really simple solving a system, as it can be a large system. It doesn't matter, and it will really efficiently apply the Gaussian elimination technique. And then we can verify what's the solution as a result of this function. And then let's verify. As we see, this is the last print statement, 0 and 2.5, which is basically as we expected for our problem. We already know what's the analytical solution here. Let's do a 3 by 3 system of equations, this time something a bit bigger. And suppose this is the matrix of coefficients. I have 3 equations, and these are the coefficients in front of x1, x2, and x3. And then you just simply need to write down the right-hand side of your problem. For example, here we had 5 and 5. And this time you need to whatever is the problem, you need to enter the right-hand side coefficients and then just call the function one more time. And basically you can obtain the result, and let's let's put a print statement here, and then let's verify. So this is the solution for x1, x2, and x3 from our 3 by 3 system. Now, what else can we do to solve the same problem? Well, actually we can remember our problem is like this. So the solution for x is going to be the inverse of a times basically b. Okay, so this will be the analytical solution actually using also linear algebra. So we can implement this actually directly. So this is the direct solution. We can call this as a direct solution because we are directly taking the inverse. In other words, we are multiplying A inverse on both sides of the equation, and then this gives us the how we can call this in a function. And basically we can again one more time print these two together and compare and verify we really obtain the same solution. As you see, all these gave us the same solution. Okay, so you can create such similar examples. Another application is basically if you have a least squares problem. Again, this is same as solving a system of equations. And you might have some independent variables. Again, you might have something on the right-hand side. And then basically you can apply the least squares method under the NumPy linear algebra solver. And again, one more time, this is just in statistics. You know how to run a regression, a least squares regression. Basically, that's what we are doing here. That's exactly the same. And as you see, we can obtain the x here, and then we can obtain our residuals from this least squares regression. Okay, so it's just another application for solving the system of equations where you can just obtain the least squares estimators. And then let's continue. There are a few more examples here where we again solve a system of equations, ax equals to b. As we said, the direct solution can also be obtained by A inverse times B. Or you can use the Gaussian elimination, as we said, using the solve. Here, pay attention, when you use this solve, basically we are solving the system using the Gaussian elimination technique in linear algebra. So here we can obtain this and then again verify these x values. So we have a 2 by 2 system as usual, and then we have the right hand side. So we can well, this is the same, sorry, I can comment out. So we can check the solution down below here. That's our x. And we need to multiply this with b in order to get the vector of x values. So the solution for the system is actually x1 is 0.6, x2 equals to 1.2. You can come up with many such similar examples. I don't need to go through all of them one by one. You can try yourself. Now, another example here for us is the Cholesky decomposition. Again, this is a commonly used function. For example, you might, in statistics, again, you might work with a variance-covariance matrix. If you are familiar, then this will be more meaningful, but if you are not familiar, then that's just an extra example for you. And like in statistics, the variance-covariance matrix, we might need to decompose it because, let's say, we want to simulate these random distributions. So in those kind of situations, a commonly encountered problem is to decompose a variance-covariance matrix. And one of the techniques that is used is the Cholesky decomposition, which is available again if you need to solve such a problem. In linear algebra, that's also available in Python. And you can directly use this SciPy package, and then import the Cholesky decomposition method function, and then just apply, and that will give you the decomposition for your system. And then you can verify these with also analytical methods if you need. Okay, so let's comment this. It's an extra example. Now, as usual, for most of the time, the basic operations you will need to do are related to, for example, matrix multiplication, which is a very fundamental operation for you, for most of you. Here you can basically define two by two matrices, and then we can just do the usual matrix multiplication. Here we multiply the first row with the first column, and then first row with the second column, and so on. So basically you can also verify this matrix multiplication. That's the last result that we get here. The last result is from this multiplication. We print the first matrix, the second matrix, and the result. So if I come below here, so this is my first matrix, the second matrix. So if I multiply my first row with the first column, right, I get 19, right? I have 5 plus 14, that's 19. So if I multiply the first row with the second column, so I have 1 times 6, and then 2 times 16, right? So that gives me 22. And then you have the second row multiplying the first column, which gives you 43. And then the second row multiplying the second column, which gives you 50. Okay? So you can just verify this easily on a piece of paper, and then make sure we get the right answer also applying this in Python. Another alternative is the term-by-term multiplication in Python. And this is different. I mean, this is different than what we do in the usual matrix multiplication. We can verify here. So this is the term-by-term multiplication, meaning that 1 times 5, that's 5. 2 times 6, that's 12. And then 3 times 7, that's 21. And then 4 times 8, that's 32. So that's the term-by-term multiplying these two matrices. And then in the rest of the examples, again, we have some matrix inversions. So now we already see how to invert the matrix. As you see, this is a 2 by 2 matrix. I can take the inverse by just using the inverse function under the linear algebra NumPy module. So that's really not a difficult operation for you. And then you can take the determinant. Again, we commonly use determinant, for example, when we check if we have a linearly independent set of vectors, for example, and we verify if a vector set of vectors is a basis in a vector space or not. Again, we check the determinant. In many applications, we need to calculate the determinant, also including the matrix inversion. We need to calculate the determinant of a matrix. So how can we do that? That's very simple in Python. Just use the determinant det method function, again available in the linear algebra with NumPy. And then basically there are a few more other examples here with matrix multiplications. So it's really quite similar. Here again another matrix inversion and determinant. Another thing you might need to create is a matrix of zeros, okay? And that's again quite convenient in Python. Just use the NumPy zeros, and that will create basically a matrix of zeros with the dimensions that you want. So this is 6 by 4 dimension, and this will create our zero matrix. So let me uncomment the previous line and then just run this again. So here I just enter. So this is the zero matrix. That's what I want to print at last here. It's a 6 by 4 matrix of zeros as we expected. What if you want to create an identity matrix? Well, it's again as expected, EYE, that stands for the identity, and then identity is always a square matrix. So just entering one dimension is sufficient. The number of rows equals to the number of columns, and this will create an identity matrix 4 by 4. Okay, and then for the other matrix operations, it's as expected. I mean, the matrix summation. As long as the dimensions are consistent, we can add two matrices or we can subtract two matrices. So just pay attention that the dimensions are consistent. Both of them are 2 by 2, so I can directly sum these two matrices. And also for regular matrix multiplication, again, just make sure the dimensions match. So the number of columns in the first matrix must equal to the number of rows in the second matrix. So as long as the dimensions are okay, our matrix multiplication will perform as expected. And notice that for term by term multiplications, we just use the regular multiplication star here, A times B. So this creates the term by term multiplication. Another common operation for us is taking the transpose of a matrix. And again, that's very intuitive. Using once we create a matrix A, obviously first we need to have this matrix A defined. And then we can take the transpose of this matrix by just using the dot and then this method T. So it's going to transpose our matrix A. So matrix determinant here, inversion, we use again linear algebra and INV inverse, that stands for inverse. And then the solve method. Okay, these are some of the very key methods, the functions that you should keep in mind in order to work with the matrices. Okay, that's all for this video. Thanks for watching.